Okay, so this is going to be the tutorial, okay, about subspaces. So examples. Okay, and let's have a look at our first question. I'm going to do two questions in this tutorial, okay? So the first one is show that the following plane through the origin okay, so the plane is a subset of R3, okay, so our subset is called S X Y Z such that X plus Y minus 4Z equals to 0 is a subspace. Okay, so if you remember in the lecture, you have seen the definition of a subspace. We say that for any vector space, a subspace is a subset that is itself a vector space under the inherited operations. So to be able to have a subspace, first of all, we need to have a space. So our space here is R3. We have seen in the beginning of the lecture that Rn is a space. So R3 is a space, and S is a subset of that R3. Now, to be able to prove that that subset S of R3 is a subspace, the set itself has to be a space itself. The subset S has to be a space itself. And we finish in the previous video the lecture with a lemma saying that to be able to prove that a subset is a subspace, we only have to prove that it is closed on the linear combinations. Is that okay? Of two vectors, of a pair of two vectors. So now let's see. Let's prove that this is so answer. So let's prove it. Before we can prove that S is a subspace using linear combinations, let's rewrite S. Okay, so we are going to step number 1. So step 1, does this equation remind you of something in chapter 1, linear systems? This looks like a one equation linear system. Okay, so let's consider x plus y minus 4z equals to 0 as a one equation system. Okay, that's a one equation system. And let's parameterize that equation. How do we parameterize it? We parameterize it and parameterize it. Parameterize it. we parameterize it by writing the leading variable in terms of the free variables. Therefore, we'll have x equals to minus y plus 4z. And now let's rewrite our set. Therefore, our set is going to be what? X, y, z. And instead of x is minus y plus 4z. Y is still y and z is z. Okay, this is the same as minus y. Okay, no, let me rewrite it here. This is the same as, okay, as minus 1, 1, 0 multiplied by y plus 4, 0, 1 multiplied by z such that y and z are free. Okay, we have learned how to describe or write down the solution set of linear system of equations. Okay, so that means our S is x, y, z. Yeah, I can write it that way, or I can just rewrite it this way. Is our set can be rewritten as minus 1, 1, 0, y plus 4, 0, 1, okay, z such that y and z are free, are elements of R. That's S. So we have to rewrite S. As you can see, the S, even our S is the linear combination of two vectors. This is our vector 1, this is our vector 2, and y and z are scalars. So we have seen in the previous video that to prove that this is a set, a space or subspace, step 2, get linear combinations, okay, of the elements of two, let's say two vectors of S, of the big S. Okay, so based on the way we have rewritten S, the subspace, the subset S, an element S, S1 is going to be a combination of minus 1, 1, 0, y1 plus 4, 0, 1, z1. Okay, what have I done there is z1, not y1, is z1. Okay, so that's our first vector. Our second vector, okay, s2, small s2 is going to be, okay, minus 1, 1, 0, y2 plus 4, 0, 1, z2. So the lemma says if this is a subspace, then it is going to be closed under the linear combination of these two. That means we need to prove that, let's say we have for R1 and R2 in element of R, if we have R1 times S1, so that's a scalar multiplication of that vector, plus the scalar multiplication of vector 2, this must be an element of R. Sorry, do we have R? That must be an element of S. That means this is going to be a combination of these two vectors, vector 1 and vector 2. Let's see if that is true. So we have r1 dot s1 plus r2 dot s2 is equal to r1 dot s1. S1 is minus 1, 1, 0. Hope I'm going to have enough space here, plus 4, 0, 1, y1, plus, this is r1, r2 dot minus 1, this is 1, 0, y2 plus 4, 0, 1, z2. Okay, so how do you multiply them together? We have r1 multiplied by y1, so we have minus 1, 1, 0, times r1 multiplied by y1 plus, okay, I think we can, I can go one step further. So, okay, what I'm going to do is r1 multiplied by y1 here, but if you look at the second term here for the s2, we have r2 plus y2, so we are going to factorize with the vector minus 1, 1, 0. So we have plus r2 times y2 plus the second vector 4, 0, 1 multiplied by r1 times y1 times y1 plus r2, no, yeah, this is z1. Why did I write y1? This is z1, sorry. This is z1. This is going to be, sorry. Okay, so we have, this is z1. So we have here for the second. Okay, so if we pick this vector, I just want to make sure that I have everything right. Okay, so we have r1 z1 plus r2 plus r2 z2, and as you can see, I hope you can see clearly. Okay, our subset S is made of the combination of these two vectors, the vector minus 1, 1, 0 and the vector 4, 0, 1. So if we pick two vectors from that space, so the first vector is there, the second vector is there. If we pick two vectors from that subset, are we going to get a vector from that subset? Yes, we are going to get a vector which is made of these two vectors, okay? Because here, look, r1 y1 plus r2 y2 is just a scalar, okay? So we pick two vectors from the subset, we add them together, we get a vector of the same structure. Is that okay? And if you remember from chapter 1, linear combination of linear combinations is a linear combination. Isn't that beautiful? When things are connected together. So, yes, we have just proved that, okay, this is a vector space. So, yeah, it is closed. Therefore, S is closed under linear combination. So combinations, if you want. So we can, this is the end of this first tutorial. Let's go to the second tutorial. First question of this tutorial, question 2. It says, consider a set L written as A, B, C, 0, okay, such that A plus B minus C equals to 0. Okay, so they are asking us to show that L is a subspace. L is a subspace, yes. First of all, L needs to be a subset of a space. And if you remember, we have seen that the set of M, the set of n times M matrices is a space. So here, the space here is a 2 by 2 matrix, and the set of 2 by 2 matrices, and L is a subset of that space. Subset, so of 2 by 2 matrices. Got it? And 2 by 2. Okay. So first of all, if you remember the way we have done it for the previous question, let me write answer here. Let's rewrite. We are going to step 1. We are going to consider again A plus B minus C equals to 0 as a one equation system, linear system, and linear system, and parameterize it. Parameterize it. So we have A plus B, minus C minus C equals to 0. So we are going to write the leading variable in terms of the free variables B plus minus B plus C. So now let's rewrite our set. So our subset L is going to be written as, instead of A, I'm going to write minus B plus C, and B here, C here, 0 there. We can rewrite this as follows. You can rewrite it as minus B, B, 0, 0 plus, okay, C, 0, C, 0. So how do we add that? Let's see. Let's check if that's true. How do we add two matrices together? We add them component wise. So we have here minus B plus C is there. We have B plus 0 is our B there. 0 plus C is there. And 0 plus 0 is there. This can be rewritten as, okay, so we can rewrite our L as minus 1, 1, 0, 0. You can factorize it or parameterize it. Okay, plus 1, 1, 0, 0, C, such that B and C are free, are elements of R. So this is our new L. So we can say that an element in L is going to be the sum of these two basic matrices. The matrix minus 1, 1, 0, 0, and then matrix 1, 0, 1, 0. So the question is, if we pick two elements from this subset, are we going to get as the same element? Are we going to get an element of the same structure? Let's check. Step 2. Step 2. Get linear combination of two vectors of L. Okay, even though they are matrices, we call them vectors. I remember. I hope I have explained it in our previous lectures and tutorials. So let's pick two vectors, v1. Yeah, let me call it v1, which is going to be minus 1, 1. It is going to be made of the linear combination of these two, 1 plus 1, 1, 0, 0, c1, and our second vector, v2, is equals to minus 1, 1, 0, 0, b2 plus 1, 1, 0, 0, c2. If we add them together, are we going to get the same structure? And here the same structure means a structure made of the combination of these two basic vectors. So let's see, v1 plus v. Oh, okay. Let's have we have our r1 and r2 from R. So let's see, R1 times V1 plus R2 times V2, okay, is equal to minus 1, 1, 0, 0, B1. So we have, it should be R1 there. I should have written R1 multiplied by all of that. We have, I have R1 multiplied by minus 1, 1, 0, 0, B1 plus 1, 1, 0, 0, C1 plus R2 dot minus 1, 1, 0, 0, B2 plus 1, 0, 1, 0, C2. Okay, so let's multiply them together. So I'm going to go straight away. Okay, so here we have we are going to factorize. So with the matrix minus 1, 1, 0, 0, we can factorize R1, B1. So we have R1, B1 plus R2, B2 plus R2, B2 plus the second matrix, which is 1, 0, 1, 0. We can factorize with the R1, C1, R1, C1 plus R2, C2, R2, C2. So yes, R1 dot V1 plus R2 dot V2 is closed under linear combination because we have is going to be the linear combination of those two vectors is a structure in R. So is the combination of these two basic vectors. So linear combination of linear combinations is a linear combination. I love that lemma, if you remember. So this is so that is, and so this whole thing is an element of R. Sorry, an element of our space, our subset L. This whole thing. This whole thing belongs to L because it is a combination of these two basic factors. And R1b1 plus R2b2 is just a scalar. Okay? Therefore, I can say, therefore, L is a subspace. Okay, I think we are going to stop here. Just a quick summary. In order to prove that a subset is a subspace, first of all, that's okay. Let's say, in order to prove that a set is a subspace, first of all, that set must be a subset of a space, a vector space. Then, if we take a linear combination of the element of that subset, we need to get an element of that subset. So that subset must be closed on the linear combinations, basically, which means it must be closed on the addition and scalar multiplication. We don't need to go through all the 10 conditions to be able to prove that a subset is a vector space. You need to prove only the closure on the linear combination. Is that okay? We are going to stop here and see you in the next video where we will continue with the lecture with the part 3. Thank you.